we have William Kinnameth available today to speak to us primarily about climate change. William is a former head of Australia's National Climate Centre and consultant to the World Meteorological Organisation's Commission for Climatology. He was also Australia's delegate to the WMO Commission for Climatology from 1982 to 98, and he served 2 4-year terms on its management board, participating in expert meetings and conducting training programs for Africa and Asia. William Kinnameth was a member of Australia's delegation to the ministerial meetings of the Second World Climate Conference in 1990 and to the Intergovernmental Negotiating Committee for the United Nations Framework Convention on Climate Change, 91 to 92. William Kinnameth has a Bachelor of Science degree from the University of Western Australia, a Master of Science degree from Colorado State University, and a Master of Administration from Monash University. He's also the author of Climate Change, a Natural Hazard, written in 2004. So welcome, William, to Seeker University and our property program. I really appreciate you making time to come along and speak to us, especially with your experience in the climate and climate change area. It's a delight to have what I would call a real scientist, somebody who's got the experience and has probably been involved in the whole global warming, climate change world, at the times when it was probably most interesting. But I'll let you tell us about that. We take it for granted now to a certain extent, but with that bio, I'd be interested in maybe your thoughts about what you found the most interesting parts of your background, or maybe the most challenging.
Well, thanks for the invitation to be on the program, Garrick. It's always a pleasure for me to talk about weather and climate, because it's been sort of 60 years of my life. But when you say the most interesting things, there's a number of interesting things. The daily weather is interesting for all of us, because we live in the weather. But I guess in terms of a professional background and my interest over the years, it's been the application of meteorology and climate to people's lives and how they prepare for things. As far as I'm concerned, there has always been weather and climate extremes, and we've always got to prepare for them. And this current fad about, well, net zero, if we bring carbon dioxide down, everything will be fine. Well, no, it won't, because we'll always have weather and climate extremes. You go back through the records, even in Australia, and there's been tropical cyclones and so forth, right back into the first records of people coming to Australia. And drought, I think the first settlements in New South Wales, they were hit by a drought. Some say it was an El Nino situation, which was they didn't understand at that time, and we don't understand a lot about that still. But these are the sort of global impacts on our climate. But we've got to be very, very much aware of those. I thought what I'd talk about, Garrick, was just do a little bit of an overview first on some of these things, and about the background of climate and climate change, and then we can get into some more details. So I'll just go into if I can just share the screen and go into this. Where are we going now? There we go. Just addressing weather and climate extremes, as I mentioned, that the most important thing we've got to recognise is that there will always be weather and climate extremes. And I think back to the story of the three pigs and their house of straw and house of sticks and house of bricks and so forth. We've got to be prepared for all of these extremes. And we've now got a lot of data, meteorological data, in which to help us to prepare for these. They give us the frequency of some of these major events. And we can use the data for the safety and building to minimise destruction. We can also use it for preparedness to what we do in an emergency. The weather forecasting service is also a vital part of what we do, because it gives us early warning. And we know now, we see in the newspaper reports from the United States, when they have hurricane warnings, likely hurricane landfall, you get these kilometres and kilometres of motor cars leaving those danger areas because they've got early warning. They can get away and come back and see what and rebuild if necessary afterwards. But you've got to evacuate. You've got to have safe passageways. So people who are involved in the emergency response have got to ensure that there is a safe passageway. People who are living in the country, when there's bushfires and so forth, that to ensure that if there's fires in the area, they have got a safety plan when things get very serious. How do they get out of it? Because I think it's pretty evident these days that in some of these most extreme bushfires and grass fires, that there's no point in staying and trying to defend. Some of these weather conditions are so extreme that then they keep the fires going. You've just got to get away. And the same with storms. And even during a severe event, you've got to have monitoring of what is going on, and the response people, emergency services, have got to understand how the conditions might be changing. So the ongoing monitoring of events is important, and providing that information to people. And trained and equipped crews to respond, they've got to understand the severity of the dangers and so forth. And of course, afterwards, there's always the cleanup. We've got to ensure the safety of the people going into those places, that there's not a new danger comes in while they're in there trying to recover what's the danger or the damage that has happened. Homeless people needing shelter and so forth, businesses destroyed, they've got to be renewed, and public infrastructure. That last one is a very interesting one that I was involved in a program of monitoring the 1997-98 El Nino event, part of the World Meteorological Activity, and came across that in Peru during that El Nino, while Australia had drought, they had very heavy rains. Now, the very heavy rains that don't happen very often, but a river flooded, washed away a bridge. Now, there were farmers and so forth on one side of the river who they had a little bit of damage, but then they recovered very quickly. But they got their crops growing, but they couldn't get to market because the infrastructure was out. And so it's important to maintain the infrastructure and get the infrastructure back going for people's ongoing security. So I want to make the point that, weather and climate extremes, they are an ever-present danger. They cause death and property destruction, and regardless of the changing climate. And there is a changing climate. It has been changing right back through the ages. We've got a lot of sort of historical information about the changing climate. We know that there was glacial periods only 20,000 years ago. Most of North America and Northern Europe was under about 2 kilometres of ice. Sea levels were about 130 metres lower than they are today. We worry about the Great Barrier Reef. Well, 20,000 years ago, it was a limestone shelf above the sea. And so climate does change quite naturally. On these very large timescales, we know there's been glacial cycles that go back for 500,000 years. And before that, they're minor cycles, but that goes back another 3 million years. But even in the last sort of 10,000 years, there's been minor warming and cooling. And it seems to be on about 1,000-year cycle. We know during the time of the Greeks and Roman Empire, it was warmer than later on. Those civilizations sort of collapsed, and we went into the Dark Ages. During the about 600 AD, there was a lot of the rivers of Western Europe, they froze over during winter. They don't at the present time. The Rhone River and the Danube, which we have lot of people go on a cruise down these rivers these days. Back in 600, you couldn't have done that. And then we came into the medieval warm period, when the great period of building of churches and castles and so forth. And then obviously there was a much better agricultural production, able to support the lives of many more people. Then we go into the what's called the Little Ice Age. And again, it was not as severe as the glacial period, of course, but it was quite severe for people. We talk about the retreating Arctic ice back in the 1600s. Winter ice came right down and wrapped around Iceland. And so, and the rivers of Western Europe again were frozen over in winter time. Not as much food production and so forth. So there's these sort of 1,000-year cycles, and we're sort of, I think we're lucky at the present time. We're in one of these warmer periods, and it's going by history, we'll get colder again in the next 100 years or so. But even so, on the shorter time scales, we have the El Nino, La Nina events, which cause such havoc to Australia's rural production, with drought during El Nino, and the present time we're going through an La Nina, and lots more rain over eastern Australia. So we've got to be prepared and understand those sorts of weather cycles as well. And then there's other sort of minor cycles. There's the sort of Atlantic decadal oscillation, there's the Indian Ocean dipole, and other sorts of factors that affect our weather. And the more we understand and know those, the better we can be prepared. They're all the natural changes that take place. On top of that is the projection of major climate change. Some call it an emergency due to increasing anthropogenic carbon dioxide and other industrial greenhouse gases. And this is supposed to have started back in the 1700s with industrialization, although the data shows that the carbon dioxide buildup really didn't get going until after the Second World War. Before that, there was an increase in carbon dioxide in the atmosphere, a small amount. There was carbon dioxide, carbon being burnt and so forth, but it wasn't building up until after the Second World War, and it has really taken off since then. At the beginning of the 20th century, there's about 300 parts per million of carbon dioxide in the atmosphere. It's well over 400 parts per million now. Now, the danger of climate change is both theoretical and based on computer models. And I'll just very briefly, the theory can be quite complex, or it can be very straightforward. I'll try and give the straightforward part because it's much easier to understand. And it all starts off with what we call the global energy budget. And this is a budget which shows the heat coming into Earth and the heat going out, and how it's changed around within the atmosphere. On the left-hand side of this diagram, what you see is the yellow arrows coming in. That's the solar radiation coming in from the sun. It's pretty constant, although the Earth is turning, and it varies from place to place diurnally and seasonally. But on a global average, it's pretty constant. A little bit of it is actually absorbed in the atmosphere. Some is reflected from the clouds, and some is reflected from the surface. But about 161 watts per meter square is actually absorbed at the surface. Now that is actually warms the surface, but actually radiates long wave radiation. And what has sort of puzzled scientists for about 200 years is why it is that there's so much more long wave radiation from the surface than what we get from the sun. How is it that is supported? And it was back in the 1820s that a French mathematician worked out that, or he surmised that what happened is that there's substance in the atmosphere that absorbs this emission from the surface, so that when you get to the top of the atmosphere, you get as much long wave radiation going to space as the short wave radiation coming in. So from a physics perspective, everything's in balance. And so it's the absorption of long-wave radiation by carbon dioxide, or the greenhouse gases, they call them, in the atmosphere that was giving the higher, supposedly the greenhouse gas acted like a blanket to keep the surface warm. Now, in the 1850s, John Tyndall, a chemist, he actually worked out that yes, there were these substances, carbon dioxide, particularly water vapor, that were able to absorb long-wave radiation. And so it sort of took off from there, that here's this theory that we've got carbon dioxide in the atmosphere and water vapor. Now, water vapor is natural, so that's essentially dismissed because it's a natural greenhouse gas, but it's carbon dioxide is where the focus is. And you have Arrhenius, the Swedish chemist, who said in 1896, well, the reason why we had these glacial periods and so forth is because of volcanic activity building up carbon dioxide in the atmosphere. When there's more carbon dioxide, Earth gets warmer. When there's less volcanic activity, it gets colder. Now, that was a good theory for a couple of decades, until Milankovitch came along and said, well, look, the glacial cycles come about every 100,000 years. How come that, why does volcanic activity come in these similar sorts of periods? And so it became evident that carbon dioxide and volcanoes wasn't the really important part. But for the next 100 years, 50 years, there was still this groundswell of people saying, yes, there's carbon dioxide, increased carbon dioxide, it is a greenhouse gas, it will change the Earth's temperature. And in the 1960s, then along came a meteorologist and a computer modeler who said, well, look, we can build a model and see what happens. And Sukio Manabe did that in America and built a model, and it turned out that if you double the carbon dioxide, the global temperature would rise by about 2 degrees. And that's been the thoughts ever since, that all the models, more sophisticated, more developed, they all have about 2 degrees on average warming, maybe more, depending on how they construct their models. But the basic of it is now that we see that the top of the atmosphere, there is as much solar radiation coming in as long-wave radiation coming out. The basic theory that Manabe put forward was that carbon dioxide, when you increase the concentration, because the emission to space is from a higher, colder level, the amount of carbon dioxide amount of radiation from carbon dioxide decreases, and therefore there is more heat is retained in the atmosphere, and it warms the atmosphere, and that's how the models work, and that's fine, except that it's very simplistic, and I'll just go through and show you a few of the problems with that sort of a model. The 3 points that we've got to make is that, one is that the greenhouse gases, they actually emit more long-wave radiation than what they absorb. And so Fourier's first hypothesis that it was the absorption of long-wave radiation that warmed the atmosphere is clearly wrong, because you can look at the diagram on the right-hand side where the Earth emits about 398 watts per square metre. Most of that is absorbed in the atmosphere, but the atmosphere, the greenhouse gases and the clouds, they emit 239 watts per square metre to space and another 342 back to the Earth. So the sum of the 349 and the 239 is obviously much greater than 398. It's so the atmosphere is actually cooling, and by long-wave radiation, and it's an important part for the meteorology and how things work. It's always been a bit of a concern to me that why is it that the people who talk about climate change continue to talk about the absorption warming the atmosphere when we've known for at least 60 years that the greenhouse gases emit more radiation than they absorb. But never mind, the models supposedly take this into account. The second point we have is that there is this radiation balance at the top of the atmosphere, and I'll just get on to that in a minute. But before we do that, the solar radiation, they say, is absorbed at the surface. Now, Earth is 70% ocean, and solar radiation is actually absorbed in the upper layers of the ocean to warm the upper layers of the ocean, and we'll come to that again. So first of all, let's just look at this top of the atmosphere radiation. If it's in balance, we reduce the long wave radiation by increasing carbon dioxide. Earth warms in response. And according to the IPCC and all the modelling, they say there's a linear response of surface temperature to radiation forcing. That's the sensitivity. And sensitivity can only be evaluated by a computer model. That means that people like myself who haven't got a computer model, I don't have a place in the game, because you've got to have a computer model to be able to work it, and it's computer models which are the things that are so important. However, if we look at the real Earth, it's not flat. It is actually round. Most of the solar radiation comes into Earth in the tropics, and we see on this little diagram, this is the South Pole and the North Pole at the top and the equator in the middle. Over the tropics, there is excess shortwave radiation coming from space over the long-wave radiation being emitted. But over the polar regions, there is more long-wave radiation emitted to space than the solar radiation absorbed. And we can work that out because it's colder in the polar regions than it is in the tropics. And so to get any semblance of radiation balance at the top of the atmosphere, you've got to transport a whole lot of energy, heat, from the tropics to the poles. And that's by the ocean and atmosphere transport, by the ocean currents and the atmosphere currents. And so immediately, it's not just a radiation problem. It's a problem of fluid dynamics. And to have a steady climate would imply that those circulations are always steady. But of course, they're not. And so we get a variable climate. And the question is, how much variability do we have? And is it changing from time to time, or is it everything returning every year to the same spot? The second point about the solar radiation being absorbed in the oceans is that, and this is a little diagram here, shows a cross-section across the Pacific at the equator. On the left, it's around about New Guinea. On the right, it's about South America. So we're talking about 10,000 kilometres across the top there, but only about 500 metres in depth. And we see that the solar radiation is absorbed in that top layer of the ocean, but it's not uniformly absorbed. Over in the east, we find that the thickness of the layers is much narrower. And in fact, the temperature at the surface is much cooler than in the west. It's in fact about 5 degrees cooler. And so there's this temperature gradient across the Pacific Ocean from east to west. And the reason is because of ocean overturning. We have upwelling of cold water in the east coming up into the offshore from South America and North America on the west coast and out into the Pacific. And we've got this cool tongue of water. Now, that varies from year to year. This is our El Nino, La Nina. When you have an El Nino situation, that upwelling is reduced. And when you have a La Nina, like now, it's increased. And so you get colder water over in the east, and you get much more airflow across the Pacific, bringing moisture to the west. But that is just symptomatic of changes in the ocean circulation. The solar radiation coming in and forming this sort of heat reservoir in the upper layers of the ocean, that heat can only go away from the tropical area in two ways. One is through the surface by radiation, ocean heat exchange, and by evaporation. And evaporation is a very important part of the heat loss from the tropical ocean. And the other point is the ocean circulations. the overturning. We talked about the cold interior water coming to the surface. Also the ocean gyres of the Atlantic and the Pacific, bringing warm water from the tropics to the polar regions and cold water down the east side from the polar regions to the tropics. And so you get that exchange of heat taking place in all of the oceans. So again, if that is, if they're all constant, then the temperature doesn't really change very much. However, if those circulations change for some reason, then you'll get changing transport of heat. You'll get changing heat content of that ocean reservoir, heat reservoir, and so you get changing temperature at the surface. Now, the reason that is important, again, we come to the Pacific, and this again is now time. We've now got 40 years of excellent observational data, global observational data over the atmosphere and the surface of the ocean. More recently, to some extent, to the depth, but certainly over the surface and the atmosphere. And what we see here is the temperature for a band of the ocean surface, 10 degrees north to 10 degrees south, right around the circumference. It's the sort of the equatorial trough. And that the blue line is the ocean surface temperature for that band. Now, we've also got the atmospheric temperature from the satellites for the same 20 degrees north to 20 degrees south. And that shows that the atmosphere temperature is responding to the surface, to the ocean surface temperature. So every time we have an El Nino, which is one of these spikes in the graph, we get a rise in temperature of the atmosphere as well. Whenever we get a La Nina, which is the drop in the ocean temperature, we get a cooling of the atmosphere. Not very much, about 1 to 1.5 degrees, but what are we talking about in terms of saving the planet? Saving 1.5 degrees temperature rise through anthropogenic global warming, but it goes through that sort of a cycle from year in, year out. So we've got to be aware that there is all this variability taking place at the same time. Now, so the ocean heat reservoir is changing the sea surface temperature with time and making it variable, and also the atmosphere. But on top of that, we've got a trend. And if you look at the diagram, it's an upward slope in the graph. It's about 0.1 of a degree per decade. And so what we can be confident on is that there is actually global warming is taking place. In the tropics, it's about 0.1 degree per decade. It will, well, the reasons for that we can look at. Some people say, well, look, it's carbon dioxide which is doing that. But we can look at the impact of carbon dioxide. To increase the temperature, you must increase the radiation emitted by carbon dioxide back to the surface to warm the surface. And we can very accurately calculate now the change in back radiation. What we've got on this table here is if we've got a standard tropical profile of water vapor, and all we're doing is changing the carbon dioxide and changing the radiation back to the surface. With no carbon dioxide in the atmosphere, the water vapor alone will give 361 watts per square metre radiation to the surface. If we go to 200 parts per million, which is the sort of the concentration at the last glacial period 20,000 years ago, you do increase the back radiation by about 7 or 6.5 watts per square metre. So yes, there is an increase. But then if you go from 200 to 300, which is from the last glacial period to pre-industrial, it only increases by 0.6. So there's very little increase in back radiation to warm the surface. And if we go through the 20th century from the 300 to the 400, again, it's only 0.7 of a watt per square metre. So it's not very much. Now, we do know also that in this period of 40 years, we can calculate how much carbon dioxide increased. We can calculate the increase in back radiation over that period, and it's about 0.35 watts per square metre. However, the 0.4 degrees rise in surface temperature means that the evaporation rate has been increasing by about 3.5 watts per square metre. So there's not enough heat coming from the carbon dioxide to generate the temperature to offset the evaporation of latent heat. So clearly it's not carbon dioxide. And so I think we're looking back now towards natural processes that are causing this warming. Now, the tropical warming has replications elsewhere because, as we mentioned, the heat is being transported from the tropics to the polar regions. And over the high latitude, this is north of 60 degrees north in the Arctic. What we've got here is the mean temperature of that part of the hemisphere, and is the orange line. And we see the wintertime in January, December, going to summertime in sort of June, July, August. It just gets above the freezing level for a few months. The blue lines are in fact the trend in temperature. Now we saw it was 0.1 degree per centigrade per decade in the tropics, much higher in the Arctic region. The average trend is 0.7 degrees per decade. The maximum warming is actually during the winter months, not during the summer months. The minimum warming during the summer months. So in the dark of winter, when there's no solar radiation coming in, the high latitudes are warming. And it's essentially because of the transport of heat by the atmosphere during those winter months. The maximum transport is during the winter months when the temperature difference between the tropics and the polar regions is greatest. And so we see that we've got a natural warming taking place driven by what's going on in the tropics, and that's being driven by the changing heat content of the ocean layer. So my point is that we've got a natural system taking place, and we've got to prepare for it. We don't know how long this warming is going to take place for. We know that it is having some considerable effects in the high latitude, and particularly for people living up there. The ice melt period is extending. So we read about how the tundra is thawing and it's causing problems, but also the growing season is lengthening because the spring thaw is coming earlier, the freeze is going later, crops can grow for a longer period. And we know from satellites that there's been an enormous greening over the middle and high latitudes of the Northern Hemisphere over the last 20 or 30 years. So there's positive benefits as well. So we've got to look at those and offset one against the other. So I guess the point that I leave with is that we've got this theory about anthropogenic global warming. My view is that there's a lot of problems with it, but we certainly have got natural change taking place, which we've got to prepare for. So I guess I can leave it there, Garrick, and we can go on to sort of discussions about how this is all impacting upon sort of people in Australia and all the sort of things that you're interested in.
Yes, no, thank you very much, William. That was fascinating. It reminds me of the first time I was exposed to anything like this, which now would have probably been about 30 years ago. And I was in an audience where I heard what I thought was a scientific heretic talking about the importance of latent heat and evaporation and the effects of the sun and so on. And that was 30 years ago, and a lot of things have changed since then. And it took me a couple of years to actually try and prove this fellow wrong, and I couldn't, which I found curious at the time, and indicated a lot of other things were odd that people were following this. And I think your presentation, and especially that first diagram, really bears some careful thought.
My views go back to in 1965, the chief of the CSIRO Division of Meteorological Physics, Bill Priestley, he wrote a very nice little paper, which was titled Limitations of Temperatures in Hot Climates by Evaporation. And he sort of pointed out that over the ocean, the highest temperature you get is about 30 degrees. In the tropical rainforest, it's about 35 degrees. Out in the savannah, it gets up into the 40s, and in the desert, it's up into the 50s and so forth. And it's all due to evaporation. It's so important to how we keep our temperature down and so forth.
That makes a lot of sense. And just 2/3 of the Earth being water suggests that evaporation really should be considered in there. It didn't seem to feature as prominently as I was expecting in your diagram, but perhaps that's because of a more complete understanding of it as time goes on.
Yeah, that first diagram, I looked at the sort of effects on the radiation, but the balance at the surface from the coming in of the solar radiation, the emission of long-wave radiation, and the back radiation, that is out of balance unless you consider the evaporation and heat exchange. And that's about 80 watts per square metre. So it's not inconsequential globally. In the tropics, it's even higher. So it's the evaporation that keeps the temperature down to what it is now.
Right. Now, that's a good take-home point. And it does seem, looking at the longer-term trends, from what I understand, that we are in an unusually warm part of the Earth's history, as I understand it. You might be more familiar with that.
No, that's right, yes.
And as I understand it, geologists, I was cutting my teeth. My first degree was in engineering, and we had a fair bit of science, so that was all exciting stuff. And in the 1970s, when I was doing that, the climate problem that we were concerned about was the coming ice age.
Because the temperatures from the 40s, as they could measure them, did appear to be dropping. And so they thought, we've passed the peak of warming and it's going to the ice age. Well, perhaps it's not for another 100 years or so. It's hard to tell.
Although it's interesting you talk, I don't want to, we might talk about this when we're talking about sea level rise, because often we're talking about preparing for or protecting the climate in the next 100 years. And so what you're saying about a likely cooling in the next century seems to be the opposite of so much of what we're doing.
Well, history shows that this warming trend will actually come to an end in the near future. Well, I say near future, the next maybe 50, 100 years, 150 years, but it won't continue forever. And the Greek Roman warm period, that stopped. The medieval warm period, that stopped. And I guess the thing point to make is that those cooler periods are much more devastating to human and biological life than the warming. With warming, we've got life is flourishing, but when it gets cold, everything sort of goes into hibernation.
No, it makes sense. I was looking at the year 536, I think, a little while ago. I'm not sure, you might be familiar with that. No. Apparently, the best view at present, and I might be wrong here, but it appeared that the volcano in Krakatoa erupted, and it sent the world into a dreadful climate change for a few years.
Yes, same in 1812 with the one of the ones that blew up in Indonesia. That again, putting all the ash into the atmosphere, that does cool. But it's interesting that you have and we've had more recent examples where we've got instrumentation where the ash has gone into the sky, into the stratosphere. The Earth is cooled, but after about 3 years, it's returned to the temperature that it was prior to that. So there's natural inbuilt physics and heat transfer that are regulating our temperature.
Excellent. No, thank you very much for that, because it's important. I mean, in the rural area, and a lot of the people who will be watching this interview will be interested in the effects on rural production and, eventually that impact on rural land values and so on, which is what we're very concerned about. We're concerned about carbon dioxide production. I was a little bit surprised when I discovered that our rural industries are one of the big CO2 producers in Australia. And I thought, crikey, how do you do that in amongst when you're growing wheat and cotton and whatnot? Could you say a little bit more, or I think you've already covered it to a certain extent, just those changes that are likely to happen? I mean, we do have carbon dioxide increasing in the atmosphere, but we've also got these more complex likely climate changes. You're saying, now if I'm correct, that the warming is more likely to occur in the higher latitudes, that's the cooler parts of the world?
Yes.
Where the tropics are probably not going to be affected as much?
Tropics will get wetter. And we know that during the last glacial period, the tropical ocean temperatures were only about 3 degrees cooler than what they are now, whereas up in the Arctic, it was probably 25, 30 degrees cooler than what it is now. So that's a big difference. And what it means is that very little can grow in a very short growing period during the summer in those high latitudes. Whereas in the tropics, what we'll be looking at in a warmer time is more rainfall. And we know that as the ocean temperature rises, the evaporation increases by about 7% for every degree centigrade. So we will get a wetter period, but of course, we'll still have El Ninos and La Ninas, we'll have droughts and so forth. But when it rains, it will be a little bit wetter. And,
okay, that sounds like it. Again, I'm just using a bit of a broad brush here. If we were to go into that kind of a world, living in Darwin wouldn't be as uncomfortable as it is at present. Perhaps you'd need a bigger boat to float to work in or something.
Well, I don't think a place like Darwin will change very much at all, in the sense that I lived up in Darwin for 4 years. And so the dry season was very pleasant. And it was just those couple of months of over the summer, excuse me, that were most unpleasant. When the cloud came in the monsoon, it was quite pleasant again.
Okay. No, that makes sense. And so likely to have, and again, I mean, we're talking about long periods of time, and this is assuming that we do get some warming in the near future, maybe in the lifespan of people that are likely to be watching.
Yes, but not a lot. Yeah. The biggest, say before, the people who notice it most are in the high latitudes of the Northern Hemisphere. I was in Geneva working in the early part of the 2000s. I happened to, there's a news item came on that they said that the growing season in Switzerland had lengthened by 2 weeks during the 20th century. And they'd worked this out by when you get the first blossoms appearing and first frosts and so forth. And so they're able to quite confidently say that the growing season was expanding. And that was before I'd done any of this work on the temperatures. But it was it's known, yes.
I understand that, now again, this is probably in a different area, we're not talking about climate, but agriculturalists are very fond of increasing the carbon dioxide in the atmosphere because it also makes plants more robust and apparently more resistant to cooler climates. So higher carbon dioxide helps semi-desert areas.
Well, a lot of horticulturalists, they actually pump more carbon dioxide into their greenhouses to increase the production of the plants, because photosynthesis, which is what plants build on, is absorption of carbon dioxide and solar radiation and water vapor, water and nutrients. That's what causes growth. So carbon dioxide is very important. And they said during the last glacial period, when carbon dioxide got down to below 200 parts per million, a lot of plants were they could hardly survive because there just wasn't enough carbon dioxide. So getting back to a point about the the farmers and so forth, and the primary producers being net producers of carbon dioxide. One's got to look at this very carefully, because they talk about cattle putting out methane and so forth, but that only comes from grass that they've eaten, which comes from carbon dioxide, which the grass has absorbed. And so it's a pretty important sort of calculation to come to the conclusion that the farmers are doing bad things for the climate. I tend to doubt that very much. And the thing that is important, though, which is has been sort of I read about being recommended, is getting more carbon into the soil. And carbon is part of the nutrients and building up of the body of the soil. So I think one of the criticisms of Australian farmers in earlier times has been that they plough and the wind comes and blows the topsoil away, and so you're losing all the nutrients from the soil. So husbanding the soil to improve the carbon content is good for the growth of the crops and so forth, even though it may not be doing very much for the climate.
Okay, no, it's interesting. So this goes back to the 90s. I was involved in the development of carbon property, and you're allowed to throw tomatoes at me for that, perhaps. And I was looking at it from a legal property theory point of view, and it was quite independent. Well, I mean, it was to make carbon an investment property right. But one of the things which became apparent in my work in that area, because we're looking at the science of it, how much carbon can you actually sequestrate in an acre of land, that we really didn't know very much. Now, this again is 25 years ago, and I assume that it's probably improved somewhat. But it seemed that the carbon you can see, let's go and grow some trees, was only a tiny part compared to what you were talking about earlier with the soil carbon, which apparently leaves it what you can see behind.
It's the getting the plant material into a form that can be actually dug into the ground and retained there, and build up the texture of the soil. That's important. If you're growing trees, that sequesters carbon dioxide out of the atmosphere, but it all does make tree trunks. And what you can do with those at the end of their lifetime, you burn them, and you can't chop them down for timber for houses and so forth, because that's environmentally bad. So, all you're doing is it's a temporary fix to take carbon dioxide out of the atmosphere into above ground trees and plants and so forth. But the important thing, in my view, is to get it actually into the soil, which does the farm good.
Okay, so sort of something like mulching or...
all that sort of stuff. Yes, yeah. I go back to experience. I was in Switzerland for a while, working for a few months, and I was on a place outside of Geneva in a sort of a rural setting, and all the cattle there in the wintertime, they're kept in barns, and there's all the what the cows leave was collected, and in the springtime it was all spread around the ground, around the paddocks and so forth. Smelled a bit for a couple of weeks, but it was all going back into the soil and building up the soil.
Excellent practice, and that would probably go back hundreds, if not thousands, of years.
Yes.
Yep. No, that makes a lot of sense. Because one of the things that came out of, again, this work with the carbon property was that we're getting power generating factories to go and buy basically forests. But at least the way the Australians doing is carbon property is only locking it up for 1 century. And so what you're saying about the trees and whether it goes into houses or whatever it goes into, I'm thinking, crocky, if we're concerned about, our grandchildren's climate prospects, and we're potentially locking carbon today that's going to be released in 21, 22, that seems to be shooting ourselves in the foot. Is that?
Well, there's two things about locking up carbon in trees is that you've got to protect the trees. And what we find is that we have bushfires, and we've got all this work going to building up the carbon in the trees, and we get a fire come through. It's all lost because it all goes back to the atmosphere as carbon dioxide again. And my understanding is that I've seen the satellite photographs of where a lot of the carbon dioxide is generated around the world, and it's actually in the tropics, in the sort of savanna regions, just after the wet season, when all the crops dry out or the trees dry out, and then you get these forest fires going through. So there's a lot of fires in those sort of subtropical areas which are putting carbon dioxide into the atmosphere. And my recollection, going back to Darwin, was every sort of autumn, was after the summer grass had grown and the winds had come along and knocked it over and dried it out, the fires would go through, and so for several months the sky was polluted with smoke because of these grass fires around. So it gets lost. If you can get it into the soil, it's much better for the soil.
Makes sense. Do you have any comments or thoughts about the current environmental controls that the farming community works within? We've got everything from vegetation management to energy efficiency and so on. Is that going to have very much an effect on the climate, even if it was taken to an extreme level?
Well, I'm not sure it had much effect on the climate, but I'm certainly in favour of more efficient use of resources. And so if you can more efficiently manage the farm and to grow and maintain the status of the soils and so forth, the things that are the basis for what's producing your crops, then it's all good. Improving productivity, improving efficiency, they're all good. But if it's only to supposedly save the climate, I have my doubts as to whether it's any good. But focus on what does good for the farm and what does good for the productivity of the farm and the efficiency and so forth. And
that makes a lot of sense. I know there seemed to be a lot of work in reclaiming desert or semi-desert areas using little more than mulching and careful ploughing to maintain the moisture content. That would seem to be more durable.
Yeah, I think so. I've actually seen some videos from China where they've been reclaiming quite a bit of the desert there with forests and so forth. And they'll go around in a very systematic way. It takes a lot of effort to do that, because you've got to actually change the water flow of the area. You've got to retain some of the water, and you've got to actually increase the fertility of the soil so that it becomes self-sustaining. But they seem to have been very successful in doing that.
No, excellent. No, thank you very much. I think we've covered a lot of ground in a very short period of time, so I really appreciate you taking the time to explain that, and especially to explain the background behind it, which is really useful. And I think any final words about climate change and the rural sector before we finish up?
Well, the first thing, the main thing is not to be too concerned about these people who talk about climate emergencies and so forth, because I don't think that's on the horizon. We saw how the climate has been changing over the last 40 years. It's almost imperceptible, and that will continue on for the next 40 odd years or so. So we're not facing any emergency at the present time. We've got to be aware that the climate is changing, that there are these variable things. We've got to be prepared for extremes, and we've got to understand them and have workarounds for them. The preparedness is half the battle. If you're prepared, you know it's coming, you've prepared all the ground and so forth, then when you get one of these events, then it's not nearly as severe as if you're not prepared.
No, that makes a lot of sense, and that's a good take home. In some ways, and I think it's probably the case in other countries as well, but Australian rural community has been very responsive to change, whether it's changing crops or changing technology, or I was up in Narrabri looking at the way that weeding is done now, and putting cameras onto sprayers. It's really clever, but it means that it's done a lot more efficiently, and farmers are very quick to pick this up. And that seems to be something that the rural community has been doing, and especially in Australia, for a long time. And we, from what you say, we're not about to have a major change come on us quickly.
No, I don't think so. No, I think also that the rural community has got to take heart from the fact that they are doing good things, no matter what the city people say about ruining the countryside and whatever at times. They are doing good things. My first years were on a farm in Western Australia, and I can recall, this is back in the late 1940s, when somebody from the Lands Department came around and said, look, rather than just ploughing as you do, contour plough around those hills and things to preserve this so you don't get the runoff. And that is a long time ago, and but they're the sorts of things that gradually make farming a much more productive and sustainable industry, and I think it will continue to be so. It'll be the backbone of Australia's wealth for a long time to come.
Thank you very much. Thank you, Willem. I think we might finish it there. And again, thank you very, very much for contributing your knowledge and, to a certain extent, your long experience in this area. So it's been a marvellous opportunity just to speak with about these issues. Thank you very much.
You're welcome, Gary.